Welcome to GovCast. I'm Ross John Fortuna. The National Weather Service is ubiquitous for its forecasts, its warnings, and its measurements. For the entire enterprise to operate, it requires a slate of systems within the NWS operational model suite, including some very powerful computing. David Michaud is the director of the National Centers for Environmental Prediction's Central Operations at NWS. He oversees strategic direction there, including governing the NWS IT enterprise architecture. He joins me now to talk about high-performance computing and the IT systems that are accelerating science at NWS and its parent agency, NOAA. Welcome to the program.
Yeah, thank you so much for having me.
So we know the NWS mission and how predicting weather and keeping people safe in extreme weather events is critical. Can you talk about how high-performance computing is the foundation for turning that data into warnings, actionable watches, and all the things that the public relies on, as well as first responders?
So when I think about actionable watches and warnings, our meteorologists really use two basic types of information. So they use observational data, so that you can think of that as like information from satellites or from radar to kind of assess what's going on at the time. But then also equally as important is being able to look into the future and predict what's coming. And they generally use as a tool model predictions or numerical weather predictions. And so that's really where the high performance computing comes in, is to generate those forecast products and the forecast guidance. At the National Weather Service, we have two operational supercomputers that we run, and one's on the East Coast, the other's on the West Coast. They are able to calculate up to 14 quadrillion calculations per second, and they have generally about 400,000 cores on each of those. And so we use those computers to generate a myriad of models to support the diverse mission that the National Weather Service has. And we do that in such a way that is, as you mentioned, the word rely and trust, right? So we have to really generate that information on time each day. And so we have the characteristics on our high performance computing that really are able to keep that system up and running on a reliable basis, and we're able to implement and make change and improvements in the models in a very reliable way. And the second component of that is just really making sure that the information that we're producing is really high quality, that we're delivering to the meteorologists. So that's kind of how high performance computing and kind of actionable watches and warnings relate.
Well, I want to talk about the global weather community, such as it were, and the need to have these finer model resolutions and how to have these more specific models. How does HPC fit into that? What is it unlocking? How are you pushing this forward?
When I think about computational power and then how that translates into scientific improvement, or maybe vice versa, so how scientific improvements and improvements to these models are pushing on the computational capacity, there's generally maybe in my mind like four areas that I think about. One of those is getting to higher resolution. So when you look at a forecast model, you really want like a higher fidelity or these model grid points to be tighter and closer together so that you can get more detail as you're looking into the future. So that really drives the computational capacity needed. So if you think about it, if you double the resolution of a model, you're really needing twice the computational capacity in the horizontal direction. You need twice the capacity in the vertical direction. You might need twice the amount of capacity for increasing the time step or the resolution of the time in the model. So that right there, if you double the resolution of the model, could mean that you need up to 8 times more computational capacity just to get that higher fidelity. Other areas that I think about are striving to understand and better represent the complexities of the Earth system. So you might get into coupled models where you might have an ocean model that interacts with an atmospheric model, or you're better representing things like cloud physics or different things like that. And so those generally drive the need for more computational capacity. Another area is looking at certainty or probabilities. What we generally do there is we run multiple models off of a slightly different starting condition, and we call those ensembles. So you might run 30 or 40 different models that start from a slightly different condition, and then you can figure out what the spread looks like across the number of hours. So if you're out 24 hours and the model solutions spread greatly, then you have greater uncertainty, or if they're a tighter couple, you might have higher certainty. So that really drives computational performance and capacity. And then the other area is just bringing in new data. So the vast amounts of satellite data or radar data and assimilating those into an initial state of the atmosphere to start the model from. Those types of improvements can really drive computational performance that you need.
Yeah, the amount of computing power that is necessary for this stuff is always a little mind-blowing because of the sheer volume of it. It's hard to comprehend. And to that end, there's more and more data coming in at all points. Radar, satellite, all kinds of sensors. So how are you managing all that data within the HPC infrastructure? And what are you doing to keep it all safe?
Yeah, it's staggering when you think about it. You're right. Like you're saying, the kind of ingest of the observational data that can come into the system, and that can be tens of billions of observations per day coming into the system. We stream that into the system and store it into the system, and then we have various quality control mechanisms that look at that data as the data comes in and assimilates it. I think what's more staggering is looking at what the models produce. So on a monthly basis, we serve out to the public and out to the weather enterprise over 10 petabytes a month of data. So that translates to well over 300 terabytes a day that's served out. So when we produce that information on the supercomputer, we'll transfer that information out to a data servicing point. And about 30 times more than what we put out there to be served out to the public, about 30 times more is actually pulled out of the edge. So one strategy that we have, and just in terms of managing that flow, is just to leverage content delivery services. So about 50% of our outgoing load is offloaded to the cloud to content delivery services. And for our web services and that type of information and the data going out, we get over 1 billion hits a day on our services, and we offload about 80% of that to content delivery services. And if that's not enough from a data perspective and volume perspective, the other phenomenon that happens that we have to deal with in terms of managing the data is that varies greatly in terms of the demand as the weather events change, right? So if you have a hurricane approaching or a winter storm approaching, the demand for our information will spike. One example I think about is back in July, we had a tsunami event, and just in that website alone, we have about 2.5 million hits a day. But in a 12-hour period during that tsunami event, we had 1 billion hits on that infrastructure. So it's really managing the volume from that perspective and having strategies to manage that volume, but it's also having the strategies to manage the variability as well. And from a security perspective, we also use those content delivery services to kind of manage any sort of nefarious activity, against those services.
Public HPC and the cloud-based stuff. I know this interview came about because you gave a talk at AWS reInvent in Las Vegas. So as the technology evolves, where are you leveraging cloud-based HPC for various workloads?
So right now, we're actively using cloud high-performance computing capabilities in our research and development environment. So our scientists are getting kind of used to and spun up and attuned to how high performance computing works on the cloud. And that's just generally working those development sort of problems. There are several different features of our workloads that exist within our environment, both operationally and in development, that we're really thinking about how we could leverage public cloud-based high-performance computing. So some examples that I think about that really kind of fit with what we're doing and then how those would be beneficial on a cloud-based HPC. One such example is on-demand workloads. So right now we actually have a reservation on our on-premises systems for up to 12 hurricane runs or tropical storm model runs every 6 hours. But we have to reserve that capacity and be ready for that at any point in the year. But as you can imagine, we don't need to really run 12 hurricane runs every day. You may not have hurricanes some days. You may only have a few that you have to run models against. And so that workload varies. And so having a more elastic sort of capability to avoid that sort of reservation is, I think, a good example of how we could leverage cloud-based HPC. Inside of our core production suite that we have models that run across tens of thousands of cores next to processing jobs that really only require a single core. But those single core jobs really require that proximity to the model and all that data being generated. So trying to really project how to architect a system that might last you 3 to 5 years and getting that balance perfect between the single core workloads and the multi-core, like high intensity workloads, that can be challenging to project out. And so on a cloud HPC system, we believe that could give us some greater flexibility to adjust with the needs as the production suite evolves versus trying to really project those and get those perfect up front. And kind of one last area that I think about is what I like to call like surge development workloads. One example of that is we may want to generate a large training data set for an AI model, for example, where we might want to go back 30 years and run the latest technology of our numerical weather prediction models and create an analysis data set that might be useful for training AI models. We don't really need to do that on a daily basis or on a yearly basis, but that's a really large resource that's required that in a cloud environment, we could surge. We could decide we want to do that. We could get the computing provision quickly rather than having to wait for it or have this disruptive reprioritization of our development workload on our on-premises systems. So that's just a flavor of some of the things that we're thinking about of how cloud HPC could be beneficial to us.
You just mentioned AI and its role in all this. So I do want to pull on that thread a little bit before I let you go. How do you see that in the future of this integration of HPC into your work and how weather is being forecasted and how those systems are being integrated?
Yeah, I think that's an evolving topic with kind of predictive capabilities, but there are some benefits. So if you look at a AI predictive model running in like an inference sort of mode, you could take, for example, like a global forecast model, and I mentioned before that may take anywhere from 15 to 20,000 or up to 25,000 cores to run over an hour and a half period. You could have a very similar model capability that runs just in 10 minutes or less on one H100 GPU, right? And so when you think about that, it provides a means to perhaps generate data more quickly and push forecasts through the system more quickly. And it's helpful in this operational paradigm. But part of the challenge is really getting the data to train the models, right? And that's really reliant right now on our numerical weather prediction models to train the AI models. And so it's a balance, right? So, the way I would see this evolve is that those predictive capabilities for AI really complement and augment the existing production suite of models that we have and give us kind of more flexibility in terms of how we operate. One thing that I always kind of talk about when we do talk about HPC is it's really exciting to talk about the technologies and talk about all the speeds and feeds. I just want to make sure in context when we think about like AI predictive capabilities or numerical weather prediction capabilities and all the technology, that really comes down to the meteorologists themselves and being able to interpret all of that information and create those trust relationships inside of the communities with the community decision makers. And so it's really like an ecosystem of support where we're trying to marry up the technology with creating really that reliable sort of trust relationship with the humans on the ground that are able to kind of create that sort of forecast to keep the public safe.
Yeah, the people are always the backbone of all these things. I'm sure the National Weather Service is no different. Thank you so much for doing this. Thank you so much for being on with me.
Yeah, thank you so much.
GovCast, along with Cybercast and HealthCast, is a production of GovCIO Media and Research. For more podcasts and to check out the other shows, head to govciomedia.com.